Serial laser. No, welcome, sir. This is your laser, you can start.
Thank you. Hello.
Email.
Okay, so my email. So you can actually, search it in the web, but still, I will give it to you. So this is Shankar KS at iasc.ac.in. So that's my email. So you may contact me at this email. So if you just search it, you should be able to see all these details in the web. So good to see Harsh, Jahan, and Anurag for joining. Good to see.
Okay.
So you can, if you have any queries, because we haven't, received any questions in the portal. So I presume that you may have some, and that's the reason why you are here. Good evening, Suji. So we would like to. Oh, voice is not clear. Okay. So is that the volume, or because I can see here the volume is really at the max. So the problem could be we have the air conditioner running in the background. It probably is giving you some noise. Is that clear, Aman? Is the voice clear for rest of the folks here? So just a confirmation would be useful. Okay, yeah, the disturbance perhaps is from the ventilation, I think, that we have. Uh, so it's rather hot now, so it's the beginning of summer, so we have our air condition on here, so that's why you see this humming sound in the background. But after a while you get used to it, so it should be fine. Okay. So if there are doubts, please post it. I'm here. Um, so last time we had very fruitful discussion. I expect to have a similar kind of a very nice interaction this time as well. Okay. Um, okay. So the assignment question, right? Harsh, you find it difficult to solve you. That's what you're saying. Uh, so let me put it this way, right? So the assignment questions are designed, at least with all the TAs, right? So they put their head together to make it interesting, right? So you need to look at one degree beyond what you see or hear in the lecture. Uh, so digest it and then perhaps go back to a question and say what they are exactly asking. Are they related, or should I think beyond what is discussed? So that's where you might find it challenging. We deliberately make it because if you just make the assignments just like recall and so on, it's not going to be interesting. I'm glad that you find this assignments challenging, but if you really have trouble getting how to solve any questions, you can always reach out to us. I have been following up on the portal, and TAs are doing a reasonable job there. I keep look at it. If there are some additional clarification required, I do do this myself. So if you really have issues, or if it is beyond what you think that you are able to handle with the lecture, please do state this in the portal, right? Or you could even send me an email. So now you have my email, saying that this problem or this concept is not clear, and so on. So we could definitely address those. And even what you could do is you can prepare this list of things that you want me to repeat, or have some additional clarification beyond the lecture that is recorded. So these are all recorded lectures, right? So without having a live or active feedback. So now is the feedback that we are getting. So what we could do is the live sessions could be utilized for that. So that was the main idea of having this live session. So we could take inputs from you and give you clarifications here. So we have one more live session in April. So 14th. So 14th April we have another live session. So mark that, and it is very close to the final assessment exam, right? So it will be very useful for you to prepare. Okay, these are all the concepts. We would like to have a little bit more clarification, right? That you want me to go over. I am more than happy to do that. But please share these concepts or the challenging topics that you want me to do it, right? So if you ask me a question right away now, then I have to set up things here to address those. So that becomes technically challenging. But if you can send me those questions earlier on in the portal, like these are all the things that we want you to go over, then we can certainly do that. Harsh, let's do that. But if it is for the assignments, because you have deadlines and so on, just drop a line. I'll be more than happy to help you out on this. All right? Because this is a specialized topic. You see, it's not basic course that I can point you to. Okay, read this book, that book, right? This is very involved and very advanced topic as well, and that's why we only get people who are really enthusiastic, right? Who are really looking at advanced technology here. So Harsh, let's do that. Um, so the next question is from Anurag Sharma. When can we expect germanium and silicon germanium facility? I don't know how you um, uh, got this idea of germanium and silicon germanium. Um, right now there are places where the silicon germanium and germanium optical quality, right? A single crystalline or epitaxial growth happens. That's in IIT Bombay. So IIT Bombay, Professor Sudasata, he does this germanium and silicon germanium MBE growth, right? So molecular beam epitaxy. So that facility is available in IIT Bombay, and we just received an epi reactor, right? Ultra high vacuum epitaxial reactor recently at Sense. All right. So this system should be up and running in couple of months because this is a complex system we are putting together. The whole idea there is to do silicon epitaxy, germanium, and silicon germanium, right? SiGe growth. So that facility should be available, this year. Right? So then, IAC, National Nanofabrication Center, will have, another core technology available. Assignment 9 is out of syllabus. Okay, can you make change? Uh, I'll have a look at it. But as I mentioned to Harsh earlier, uh, there are certain things that we cover, and there are certain things that will have a string and goes beyond what we actually discussed, right? So this is the whole idea of this is to the assignment is to push the learners to go beyond what you have in the video lectures, right? Let me have a look at the questions. I will certainly re-look at it. I did have a look at it before it got published, but let me see how far we have stretched. If it is too much, then we'll certainly make changes. But my at least my bad memory tells me that we have pushed it a bit. There is no doubt about it. But I will not go to an extent saying that it is completely out of the topic or syllabus. Okay, let me have a look at it. Aman, we talk about advancement in the LiDAR and optics and photonics for smart mobility. Smart mobility, interesting. Uh, so smart mobility, when you say mobility, there are different type of mobility. Uh, so one is autonomous vehicles. See, that is where the LiDAR technology comes. So there are the LiDAR technology is not very new, let's say, right? But the application is rather new. We are using it for mapping, and we are moving into what you call the high volume use of this technology. So what is the advancement there, right? So basically what we do in LiDAR is you shoot, light, and then you capture reflection, right? So you want to know how far the object is, right? So based on the reflection, there are different methodologies or techniques that one can use to measure the objects, right? So one is reflection based on time of flight, and you can also do phase, right? There are different mechanisms that one can use in order to do this. But recently, the hardware itself, right, is changing. If you look at the early days of this Google, right? So Google used this LiDAR technology to map a lot of all the street views and everything. And even today, the LiDAR technology, it has a huge head, right? Shoots light across, so 365 degree it rotates, and then it's trying to look at the profile. The other way to do that is if you want it to be static, then the LiDAR system, right? The head will become very large, right? Based on the area that you want to cover, right? The angle and the cover, the field of view uh, will be very, if you want it to be large. So the system will be very large. So in order to reduce that, what we do is we make it small, and then it starts rotating. It's scanning. So the easiest way is to mechanically rotate it. Right? So the rotation gives you, all going all around. The other way to do that is by using micro mirrors, right? So you can use a small mirror, and then you can reflect the light. So you can reflect the light so that you get a certain field of view. But that is limited. We have these projector systems. They use DLPs, digital light processors. It's basically micro optical optomechanical structures, right? So they are all small mirrors, right? Few tens of millimeters, tens of micrometers, depends on few tens of micrometers, not millimeters. They move. Okay, this gives you a certain field of view. Now, the technology that LiDAR is moving towards is without any mechanical motion. We don't want any movement. Any movement creates, wear and tear, right? Over time, you will lose the resolution, right? You have to apply different voltages and so on in order to move these mirrors. The idea is it possible to do movement free, right? Static LiDAR system. And this is something again used in radars, right? So there is synthetic aperture radar that we have, or phase array radars. So where the radar signal, right, the scanning is shifted based on the phase, right, of the different elements in the radar. So the radar has number of antenna elements, and each antenna element will have different phase. Based on the phase front, if all the phase is equal, the phase front will be flat, so there is normal signal that is going out. And if you change the phase between left to right, then the phase front will have a left hand tilt, so the phase will move this way, right? So you are scanning, from left, and you can do this to right, right? So this is something that is already done in, uh, in phase array antenna system. So the idea here is it possible to do the same thing with light? Right? In LiDAR, now the technology is gravitating towards movement-free, uh, scanning. Right? So there we all know the phase of light can be controlled by changing the effective index, right? Effective refractive index. So if you take a chip, you can have different arrays of waveguides, and on each waveguide, if you put simply micro heaters, right? We talked about thermo-optic effect, right? So when you apply heat, the refractive index of the material will change, and if the refractive index of the material change, then the phase of the light propagating through that waveguide is going to change. And based on this, you can make LiDAR systems that doesn't require any moving parts. So that's what we are moving towards. And there are other interesting things when you talk about mobility and imaging and so on. There is something called multispectral imaging that we are doing, right? To actively look around, right? Things that are hidden, you can bring them out. So this is all in the field of imaging. Multispectral imaging meaning I don't just look at visible spectrum. I can look at infrared or mid-infrared, shortwave infrared images, so I know actually what is happening, around me. So that is the vision system that we can use for really demanding mobility application, both for civilian application and also strategic application and security applications. Uh, So then we have a comment from Tariq. Tariq, there are multiple simulation tools, softwares that are available. So this is something that we also discussed in the last, live session as well. There are loads of it. If I can name few, like you have photon design tools, right? Photon design, synopsis-based tools, synopsis tools. We have ANSYS, numerical, and then you have some free softwares as well. So Synopsys has a free software tool, Opticis, I think, and then Optisim, I think. And then we have MEEP, right? MEEP is an FTTD, a little bit heavy. It's not very easy to use. Primarily used for periodic structures, not necessarily circuits, right? Like photonic crystal, DBR, or reflectors, and those kind of things we can use. Um, and the other tool is Camphor. There is Lucida Photonics tool, and we have VLC, a photonic tool, or VPI, not VLC, VPI. There are multiple tools. They are literally doing similar kind of things, right? My suggestion would be to just take some open source softwares like Camphor to start with. It is FD tool, or some other tools that are openly available, like what I mentioned earlier, to start off, right? So that will be very useful. And you can also develop your own very simple FD tools. It's not very difficult. You just search it in your MATLAB repository. You will find loads of solvers already available. So you can build on top of that as well. So that those are all the ways that you can get your hands dirty with design. How complicated is it to design photonic IC than normal IC? Okay, so photonic IC design, and I presume normal IC here means electronic ICs, right? So the electronic IC and photonic IC designs are very different. Um, Electronic IC design is much more mature. Uh, we can just do drag and drop, and then rest of the things, the connections and everything are taken care by the software itself, right? So the connectivity check, the design rule check, it's all already very mature. Photonic IC design, right? It's not that straightforward, and there are tools now available that almost resembles electronic IC design tools. For example, we have Metagraphics tool. It has a hybrid design. You can co-design photonic IC and electronic IC in the same tool. So in those tools, you have this PDKs, right? Process design kits. You can drag different components, put them, connect them, just as if you are connecting two blocks together. Just draw a line. But then there is an algorithm in the background that takes care of how the waveguide should be, what should be the bending radius. So all those things are taken care, and it will give you a layout that is optically, let's say, feasible. For example, we all know, you can make a 90-degree bend in an electronic circuit, right? Because the wavelength of electron is so small that this 90-degree bend will not affect the electrons flowing through this, right? But then you cannot use this 90-degree bend for light, because we know it's a very strong perturbation. So you need to have a slightly angled, or it should be a a curved bend. So there should be a bending radius. So how do you make this decision, right? So that is what the algorithms behind this layouting tools work. Like if you join something like this, it will assume that, okay, you want to join component A and component B, right? So he wants to join, but I cannot allow this joint to be 90 degrees. So the algorithm will take a decision that I should give it a certain radius. So that certain radius will avoid any losses, right? So in terms of maturity, photonic IC design and electronic IC design are, the photonic IC design is coming very close to what it used to be, in microelectronics, probably 10 years ago, let's say, right? So we are the platform is there. A lot of this EDA tool vendors are integrating this design aspects in their tool, so it's mature, I would say, right? So now you can go and use Metagraphic tool to design a photonic IC. So it's available right now. So how reliable are photonic circuits in radioactive environments and deep space exploration? A very, very interesting question, Siju. So, uh, before going into reliability, let's look at what do you expect to happen, right, when there is a radioactive environment. So this is all going to be photons are very high energy, right? So they are the radioactivity means you have energy, you have particles of very high energy, right? So when they have very high energy, you have, the implication on this interaction, right? So your wavelengths are going to be smaller and smaller. Got it? So when the wavelengths are shorter and shorter, what will happen? Your strong material aspect comes into picture. So they will try to interact with the material, bombard with the material system, and that would result in reliability concern of material degradation, right? So, but there are ways to handle it. It's not that there is no way that we can operate this in harsh environment. In fact, the photonic or dielectric waveguides, they do much better without any problem in harsh environment than the semiconductors. So the effects depends on the level, but the shielding and also the packaging that we do, the coating that we do, that should take care of the exposure to the radiation that you are talking about. Deep space exploration, a similar kind of thing. It's not going to be as harmful as handling a radioactive environment, right? It's reasonably forgiving, but there is always a way to shield and protect the circuits from this very high energy radiation. So is birefringence related to optical power? If as could not could not polarization splitting depends on optical power. All right. So there are two things, right? One is birefringence. So birefringence, as we all understand, is the difference in the material refractive index as a function of orientation. So in one direction, you see nx, one of the principal axis with a certain refractive index. In the other direction, ny. Let's say ny is not equal to nx. So this is the condition where you will see birefringence. The question here is whether optical power, high optical power, could induce birefringence. Right? So the answer to that question is no. The birefringence, you don't expect to induce birefringence by just optical power, right? So how are you going to deliver the power? Right? So you have let's say you start with a material that is isotropic, right, where nx and ny is equal. So now I am cranking up the power. So that means I have a certain polarization of light, and I'm going to pump more light into the system. So there should be a transfer of energy from my optical signal to the material system, and that can happen at really high powers, right? So that energy translation can happen at high powers. So your nonlinearity comes into picture. So here the epsilons that we are talking about, right? So the epsilon x, epsilon y, and all those things, so they start to react. Okay. So now you start off with a uniform material. So that means the energy distributed across will also be uniform. So they all will react uniformly. But then you take an anisotropic material, and then you apply this electric field and you increase the field. So then there will be a proportional difference. The material is already birefringent, right? But then your epsilon x and epsilon y will change appropriately. So if you look at the displacement field, right? So D equals epsilon x Ex, right? And then you have a displacement current D2 or dy will equal epsilon y Ey. So now if I increase the power, so there is a Ex field is increasing. So that means dx, the displacement current along x will increase, right? So while you increase the power there, because already it's birefringent, right? And you cannot make an isotropic material become birefringent, right, as a material system by just increasing the power, right? And you rightly said in your second part of the question that if that is the case, then you should be able to do polarization conversion, right? So this happens in already birefringent material. So at high powers, you do see polarization effects becoming much stronger. Okay, so that is a possibility. But if you take an isotropic material, you are not going to convert an isotropic material to an anisotropic material because you know of the reciprocity that you have between the three principal axes. Okay, I hope that answers the question. Next is from Aman. It's too far. I'll have a look at this. Aman, I've been trying to contact you on LinkedIn. Okay. Yes, Aman. Let me have a look at that. I will relook at it because I hardly get time to go through everything. But let me have a look at it. Thank you. Uh, Next is all right. Thank you, Anurag, for that comment. Camphor is reasonably simple to use, and it will give you a very a nice understanding because you don't need very heavy computation capacity. You can run it on your simple PC or laptop. That should work. Okay. The next question is from Jihan. Very recently, ISRO made an announcement of quantum space communication. Does that involve photonics, like photonic qubits? Yeah. So if it is in free space, they what they have done is a free space uh, QKD, right, quantum key distribution, which is done using optical qubits. That is true. It uses optical photonic qubits or photon. All right. All right. So this is the question about uh, why refringence coming from the Kerr nonlinearity. Yeah. So the polarization that you talk about, right? So as I mentioned, you could have different polarization having a different level of Kerr gain in the material based on the system that you use. For example, if you take a waveguide where you have both transverse electric and transverse magnetic, and you are increasing, one will have a better Kerr conversion compared to the other, right? Because basically the conversion efficiency depends on the overlap that you have with the system. Okay, so it is not possible to have such thing, right? Because the power requirement for these two are going to be very different, right? Because of the field optical field overlap that you have with the waveguide system. So um, that is the reason why you won't be able to have this high intensity, and suddenly you can go from one polarization to the other polarization. What one could do though is you could have, for example, instead of having a directional coupler, you can think about having polarization conversion. What you could think about is creating phase matching, right, by using optical nonlinearities. A simple example is two photon absorption, right? When you have very high optical intensities, and the two photon absorption will induce a free carrier generation, and that will induce a refractive index change, and that refractive index change could enable phase matching. All right. So there are ways to achieve this. So for example, you can take a cavity, and then you can have this cavity work for a certain polarization in a linear region. And then when you pump it hard and you move it to the nonlinear region where your phase matching within the cavity could be changed, and now instead of resonating for a TE mode or TE polarized light, it can resonate for TM polarization as well. So these kind of interesting things could be achieved by inducing nonlinearity. So that is a possibility that you can do. The next question is from Subhash. Okay. I'll come back on that INUP present program. Okay. So I was a little busy this month. You will hear from me this week. Okay. Thank you. I was expecting this from you because I promised I would do something in March. Right? We are still in March. We'll do something. Good. Aman, thank you very much. I'm glad that you are enjoying the course, and I hope that it inspires you. Okay, Suju, it's an interesting question. Electro-optic tensors, can we tune it by nano-patterning the material? Oh, so this is the thing, right? So when you talk about electro-optic tensors, right? We talk about the three-dimensional matrix, right? So we don't really look at it in three dimension. We just look at the plane, but then the matrix is three-dimensional in nature, in reality. So your question is it possible to make nano patterning, right? So now we are talking about bulk. So is it possible to make nano patterns and then tune it locally, right? The individual patterns you want to tune it, right? So that I think that's how I understand your question here, right? You can pattern it and you can tune it. All right. I'm going to remove that nano. Okay, so you can pattern the material, right, and then you apply an electric field in whichever direction you can put it. Lateral electrodes, top-down electrodes, right, or electrodes at certain angle. It depends on how you want to exploit the tensors. Okay. Uh, Now, if I add nano to it, that means you are having very small, electro-optic structures, right? So now the question is, can I manipulate each of these nano patterns individually? The answer to that is yes, you can do it, right? So you can have really nano patterns and you can control it. But there is a catch to this. The catch is you should be able to individually address those nanoparticles or nano structures, right? So the way that we do it is by applying an electric field. So the electric field, we should be able to apply electric field to one of the structure or one of the nano pattern without affecting the other, right? So you already said it's nano pattern, right? So I'm assuming that you're talking about tens of nanometers. So now my field should be discretized in this 10 nanometers, right? I can have digitated electrodes, right? So now my constraint is each electrode should address one of those nanoparticles, right? So my electrode should also be that small. And if I have hundreds or thousands of these nano patterns, I also need hundreds and thousands of these fingers. And even more demanding is I should be able to individually address them. So my control system becomes, really hard, practically speaking. Uh, in principle, right, it is possible. You can pattern it and individually tune those. But then implementing it is going to be a challenge, but you can certainly do it. There are a lot of interesting things you can do with it, right? Uh, just to give you an idea, instead of using electric field, you could actually use optical non-linearities here as well. You can make these nano patterns of different sizes and illuminate it with high power light source, right? And they will all, confine at different power levels. And because of this different power levels, right? And I already mentioned this is high power. Then you will have non-linearity in these small pillars, and this non-linearity will be very different. Okay, so you could have there is a whole field of nonlinear imaging, right? So nonlinear optical imaging exactly does this. So based on the local structural property and the light, you can have very nice imaging that you can do, which will be beating our diffraction limit. That's good. Quantum optics is emerging so quickly thanks to our understanding of non-Hermitian systems like that. Two. One more question puzzling while designing evanescent coupling system. Most of the time people have chosen to shorter edges for this purpose. Why not longer edges? Um, I am not sure what you mean by um, the edge here. Anurag, the edge meaning uh, is it the overlap, the coupler overlap? If you are saying that if the edge is your overlap, then the main reason why we always want to have shorter coupling length is to reduce the size of the device, right? The coupling device. We don't want it to be longer. There are two reasons for that. One is when the light is propagating longer distance in any waveguide system, there is associated transmission loss, right? Propagation loss. So if you make them shorter, your propagation loss will be reduced. So that's why you can reduce the length, and then you can bring them closer, right? So these two go in opposite direction, right? If you look at the couple mode theory discussion, so if the two waveguides are there, you can bring them. If you want to shorten their overlap, then you have to bring them closer, okay? And if you want them to be far, I mean, if it is too close, maybe you won't be able to fabricate. There are some challenges. Then you have to move out and then make it longer, right? So this will help. Right. Jihan, I'm not going to cover quantum optics in this course because this was primarily photonic IC design course, but quantum communication or quantum information processing actually uses photonic ICs. So now we are working on a program where we are trying to develop quantum photonic ICs, right? Where we want to realize this huge, lens, reflectors, all those systems on a big table on a chip, right? So that there is a possibility there. But this course is, looking at the foundation or understanding photonic IC. So I'm not covering quantum, photonic ICs in this particular course. Perhaps some other course. Um, Good. I see. So, Siju, this uh, I think what you are trying to say is when you pattern it, you are going to bring in some additional terms to the tensor. That's if that is what you are trying to do. Uh, so it depends on the scale that you are talking about, right? You can you can induce this patterning, but not necessarily the conventional, structural patterning. What you could do is material patterning, where you could grow nonlinear crystals or nonlinear materials with slightly different orientation or polarization right? So if you do that, so that means you are actually patterning the polarization within the material system. So you won't be able to globally define this tensor, right? So you can have this uh, 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 textured or patterned tensor. So that's an interesting idea. It is certainly doable, and people have tried it on some other domain and application space. But it's an interesting idea. But you you cannot do this and make it, you know, um, uh, let's say. Measurable or have some effect on its tensor using conventional patterning, right? It need to be really, really small. That means you need to have sub-wavelength regime where the field should overlap on these different structures. But when you make the nano patterning, right? You can have sub-wavelength patterning, so that is still okay. You can do that, but then you need to fill the gap between these two with a material index, right? That is similar or equivalent to your surrounding medium. So then you will avoid the effect of this patterns on the propagating wave, right? So you want to avoid it if you want to exploit that. So it is certainly doable. That's actually a very good question and thought there. Uh, Priyanka Kumari has a question. Currently, I'm doing research on photonic crystals, and this course has helped me follow an important concept. Expect course on photonic crystals. Okay, I'm glad. Thank you very much, Priyanka, that I found that you have taken this course and found it useful for your understanding. The photonic crystals are class of structures that are periodic in nature, and I don't see a separate course on photonic crystals. However, nanophotonics or nano and micro photonic structures could be an interesting course that will have photonic crystals as one of the important topics that one can study, because photonic crystals there are of many kinds. There is one-dimensional photonic crystals, two-dimensional, three-dimensional, and there is quasi-crystals, right? And so on. So there is a lot of interesting things that one can study about photonic crystals, uh, but not as a separate course, I would say, but perhaps a short course, like a 4-week course on nano structures that includes photonic crystals is not actually a bad idea. Thank you very much for that interest. I'll think about it. Programmable photonic integrated circuit. So that's the programmable photonic ICs been there for a while. Recently, I mean, there are a lot of interesting works happening, or at least you can hear about it. The reason for that is the maturity of the technology, right? Uh, so we did not have field programmable gate arrays. We call it FPGAs, right? So FPGAs are very versatile tool that came into existence, not more than 20 years ago, right? As a full-fledged platform. The reason for that is microelectronics really mature, right? And we had platform to do all kind of this interesting experimentation by using this FPGAs. A similar kind of thing is happening in photonic ICs as well. So now we have a maturity level so that we can do some dynamic experimentation using this programmable circuits, right? So that requires uh, a technology that can deliver uh, the components, the elements that is required to configure, right? It's not device anymore, right? It's not a single device research anymore. It is a circuit and system level research. So for any system level or circuit level research, you need a reliable platform to work with, right? And that's the reason why FPGAs are very popular. You can buy it easily, and then you can do all kind of developments there: algorithm development, processing development, all kind of things you can do it with that platform, because that platform is much mature and reliable. Similarly, if one wants to do a programmable photonic IC, a stable, reliable platform should be available. In the absence of that, it is very hard to use that hardware. But there is another area in programmable photonic ICs that one could attempt is on coming up with different architectures. What are all the different circuit architectures or configurations one can use in order to realize various functionalities? For example, I want to realize a Mach Zehnder. I want to realize a ring resonator. I want to realize a simple 50 by 50 splitter. So how do I do it? So the circuit is fixed. I need to reconfigure. So what should be that circuit? What should be that gate, or what should be the device arrangement or mesh? That is a very interesting problem to attempt, right? So there is graph theory that people used to do that, and that area is something that one can attempt. Okay, so that will be my answer to that question. And you can definitely, it's rich. You can definitely look for funding opportunities and so on there. Okay. All right. Good. Then we have in multi-core erbium doped fiber amplifier, how to calculate OSNR. So this is very specific to optical fibers. So I'm not going to go through that question right now. How you're asking me to calculate the OSNR, uh, which is something that we don't discuss in this course. Probably optical fiber communication, or I'm not sure whether Introduction to Photonics course covers this. This is something that I can direct you somewhere, but we are certainly not in the fiber space in this course. Interesting question, Rashid. Very interesting question. Is it possible to handle high powers in photonic ICs? So, what is limiting us in handling high power? Right? Let's think about it. So, when you take a waveguide, right? Then you put energy into this, and you confine the light and its properties. So we need to look at why uh, one should be worried about increasing the power. One, at high powers, you start to see non-linearity. So what is the problem? So non-linearity will result in new frequency generation, reflection. You could have stimulated Bernoulli like effects. You could have Kerr effect, creating spectral disturbances. So those are all the reasons why high power are really challenging when it comes to uh, uh, putting high powers in photonic circuits. And the other thing is absorption loss. So when you have very small absorption loss, um, even very small absorption loss, with high powers, the energy dissipation is going to be very high. That means the whole circuit will heat up and they will give up, right? So one can do watts of power, that definitely you can do. Kilowatts are going to be difficult or not possible, for the very reason that the effective areas are very small. The power density is very high. When you say 50 kilowatts, right, you are talking about you know uh, gigawatts of power, right, inside the waveguides. So that is going to create huge absorption and scattering loss that is going to affect or kill the device. Okay. Uh, Yeah, you can do that. You can have self-focusing effect when you have these kind of guided wave system. That is certainly possible, and it actually happens. You can certainly do that. All right. Good. I think we have spent a very effective 1 hour. Thank you everyone for joining in and for active participation. I really appreciate everyone here. I see a lot of new people come in. Okay, from last time. So welcome to them and thank you for joining. And also I appreciate people who have been constantly engaging with us through the portal and also through the live sessions. Very fruitful. I'm glad that we are having an excellent learning here. Thank you very much, Harsh, for the comments. I really appreciate it. Thank you. So we will close this session. Thank you very much, and we'll meet each other 14th of April. All right. So till then, make sure that you collect all your questions. You can post it. And if you don't get the answers, keep it there so that we can discuss it in the live session. Okay. So that's going to be our last chance before the final exam, right? So you get maximum out of it. And even with not for exams, if you have another other interesting comments or ideas or any queries that you may want, please post. Thank you very much. Have a good day. Okay. So you have to post all of this in a Google form, right? Whatever your queries that you may want, right? So I was told that that is a better way to do that. Okay. So stay safe. Take care. Bye.
Yes, sir. Done, sir.